I did want to have a quick discussion. It's possible that on the homework you might encounter something that looks vaguely like this. And this is coming from our method of reduction type thing. And the question is, how do we handle this right-hand side? The left-hand side we feel pretty good about. I think we are like, take the determinant, life is good, no big surprises as it turns into differential equation looking thing for x, involving the derivatives of x. The question is, how do we handle the right-hand side? Now, a lot of you are probably looking at that question saying, is this even a question? I mean, is there something going on here that we're missing? It seems like, okay, we'll take the determinant and life is good. And so is there any subtlety? Well, I do want to say there is a little bit of subtlety here. Because, well, let's just remind ourselves about D. When we talk about D, what is that? It stands for take a derivative. And so there's a particular name attached to this. We call this an operator, which is something which operates on something. And so when we look at this determinant, we could look at it and say, well, there's really two things that could happen. It could be e to the t times d plus 1 and subtract e to the 3t times 3. Or maybe it should be d plus 1 times e to the t. Then we subtract 3 times e to the 3t. All right. Now the question is, which one is right? And how do we figure it out? What do you think? Some people say the bottom one. All right. Anyone say the top one? I'm not saying that the answer is the top one. I'm just curious if we can create controversy. You know, like, All right. And I think it's fair to say probably a lot of people are like, I'm not sure. You've made me doubt myself. Let's undoubt ourselves. And let's think about what's going on. So if we look at this expression here, e to the t times t plus 1 minus e to the 3t times 3, and I ask a question, is this a function or is this an operator? What's the answer to that? I hear function, or it could be it's an operator. Now, why is it an operator? You see this d here? In order for it to be a function, what needs to have happened to it? It needs to have operated on something. There's nothing for it to operate on yet. It's an operator waiting for something to happen, waiting for something to show up. What about down here? Is this a function or an operator? This is a function. And what's the difference? Well, see this e to the t? The operator can actually do something to it. And so it's processed. This has nothing to process. It's waiting for something to show up. This, I can actually process something, and so I can come up with a function. In particular, can anybody tell me what this would be? Yeah, it's 2e to the t, because if you multiply out, that's d e to the t plus 1 times e to the t. The derivative of e to the t is still e to the t. So it's e to the t plus e to the t, which is 2e to the t. So it becomes a function once you apply the operator. Yes?
If this side of the equation, there was that determinant, and then it was x, like it was multiplied by x afterwards, could the operator option be a solution?
Well, yeah, if there was something else here for it to operate on, because we haven't come to this side yet to help us answer the question. If there was something for it to operate on, then yeah, we would be fine. Let's come to the left. Now, just the determinant. Don't worry about the x part. When you take this out, what does it become? It's a polynomial in D, which is, in terms of our discussion, is that an operator or a function? Just a polynomial in D is an operator. It needs something to process. But good news, what do we have? We have x for it to process. And so once it processes, what does it become? It becomes a function. So, back to our first question. Which one of these two is the right one? Well, what we do is we say, I need it to look like a function. In other words, if I have an apple on the left, I better have an apple on the right, because they're supposed to be equal to each other. So the thing which looks like a function is that. It's an actual function. So this is the correct way to do the interpretation. So it's a little bit of a subtlety that we didn't talk about in class, but I just want to, if people are scratching their heads, why is this? This is why. Is there a question? It looks like there's a question.
So we could do like algebra of we have an operator on one side and an operator on the other side, and they should be equal.
Right. If both sides were operators, yes, then they should be equal. But the punchline of all this is, how do we know which way to interpret it? And the answer is, we say, what makes it so that both sides are the same type of object? And that's the correct way to do the interpretation. So that's what's going on. And so that's sort of the fun part of today, right? All right, makes sense. Apples to apples. Good. Okay, now the next thing I want to talk about, well, let's just jump into our example, and then we'll get to that next part in a few minutes. So consider the first order system. X prime equals, and there's a matrix here, 4 minus 3, 6 minus 7 times x. Now, when you see this, you should understand, there's this sort of implicit understanding that this vector x really is two pieces. And the book does this really strange thing which can help confuse us. So I'm going to explain why the book is doing it and why it's not confusing in the book, but it is confusing when we write it down. They often put x1 and x2 there. And you might be saying, but wait, don't we have x1 and x2 there? Yes, and this is where the book can kind of cheat a little bit. Notice something about this x1, or this x. What do you notice about this x? Yeah, it's a bold x, very assertive. Look at me, I'm bold. And this x, you can't tell. But see, what really happens is that when there's a vector involved, it really should be a bold x. And when it's not a bold, it's a function. Unfortunately, it's not clear when you're writing it down on a piece of paper. But if you're reading the book and you start saying, boy, I see x1 meaning two different things, look at the x1 in the font and say, is it a bold x1 or is it not bold? Whenever you see it bold, you should think vector. In particular, you should think of it as a vector function, a function where each piece of it is its own function. If it's not bold, you should think of it as an individual function. So, when you see something like this, you should really say, oh, there's really a vector here composed of two pieces, and we're really trying to solve for what does that vector look like. So that's our goal. Now, we don't have the tools to do that. We'll get the tools this week, and we'll expand them over the course of the next week and a half. In 2 weeks from now, we'll be into a totally different topic. So we only have this week and next week left with systems. So let's enjoy our time. It's going to be fun. All right, so what can we do? Well, we can talk about verifying. So that's what we're at. We're not at the point where we can find the solutions, but we can verify the solutions. Okay. So we have two candidates. So the first vector, x1, is 3e to the 2t, 2e to the 2t. And the second one, x2, e to the minus 5t, 3e to the minus 5t. All right. Well, what to do? It's not so bad. What do you do if you see the word verify? What's the thought process? Plug it in. You plug it in and you see, does it work? All right. So we'll start here with our x1. So we're trying to verify. So we'll say, all right, we'll compute x1 prime. Well, we can do that. What's the rule to take the derivative when you have a vector involved? Entry-wise. One entry at a time. The derivative of 3 times e to the 2t? 6 e to the 2t. The derivative of 2 times e to the 2t? 4 e to the 2t. Yeah, that's not so bad. Okay, so that's x1 prime. And our question, and we'll put here, does this equal question? Because we don't know yet, so our question mark, that's our goal. Does this equal what happens when we multiply 4 times minus 3, 4, negative 3, 6, negative 7 times x1. That's 3 e to the 2t, 2e to the 2t. So again, I really should have added a little step here. This is x1. All right. Well, let's multiply this out and see what we get. So this is matrix multiplication. So we're going to go along the row in the first, down the column in the second. So we're going to have 4 times 3e to the 2t, which is 12e to the 2t. Then we're going to have minus 3 times 2e to the 2t, which is negative 6e to the 2t. 12e to the 2t subtract 6e to the 2t will give us 6e to the 2t. All right. Now we go to the next row. Work our way, all right, across on the first, down in the second. 6 times 3 is 18e to the 2t. And we're going to have minus 7 times 2 is minus 14e to the 2t. And if we put that together, what do we get? We get 4e to the 2t. And what do we see? They match. Yay! Woohoo! Match. And that makes us happy, because that means it's a solution. All right. So that's the verification for x1. Now, before we go tackle x2, I want to point something out. We learned about this idea of scaling a matrix. So scaling a matrix, you can go in and multiply all the entries by a common term. Well, you can also pull out common terms. So that is to say that our x1, is there any term in common among these entries? E to the 2t. So it could have been written as e to the 2t times 3, 2. And sometimes when you write it in this way, it can make some of our computations look simpler. For instance, our computation here could have been written as 4 minus 3, 6 minus 7, e to the 2t, 3, 2, because I'm just writing what x1 is. And then just say, well, look, that constant, well, I shouldn't say constant, that scalar can come out in front. So you really are taking e to the 2t times 4 minus 3, 6 minus 7, 3, 2. And now this computation it looks much friendlier, because there's not as much floating around for you to keep track of. So that's an option to keep in mind. So we can pull out common factors. So let's do that as we go through and do x2. So we want to, because we have to also verify x2 as a solution. So x2, what is common with x2? E to the negative 5t. So we can pull that out. So e to the negative 5t, 1, 3. Okay, so what is x2 prime? Now, we have two ways to think about x2 prime, so we can take the derivative in either case. Which way do you want to take the derivative of? So if we pull out the e to the negative 5t and take the derivative here, well, you should think of this as a function times a function. I'm going to put function in quotes here, This is really a constant for all intents and purposes. Because if you took the derivative of this, what would you have?
0.
You'd have 0. So what's the derivative of e to the negative 5t? Yeah, minus 5 e to the negative 5t, 1, 3. So there's our x2 prime. And now we ask the question, well, does this equal question for negative 3, 6, negative 7 times our x2? Well, again, I'm going to use it in this format where I've pulled out a scalar. E to the negative 5t, sorry, e to the negative 5t, 1, 3. Okay, well, that's e to the negative 5t times 4 minus 3, 6 minus 7, 1, 3. Well, okay, let's do that computation. So we're going to have 4 minus 9, negative 5, 6 minus 21, negative 15. Now, are these the same? Now, they may not look the same to everybody. How can we convince people that they're the same? Why do they look different? Because you pull stuff out. So you can either put stuff back in or you can pull stuff out. So for instance here, suppose I started with the end. What would I pull out to make it look like the start? Negative 5. So you could say this is negative 5, e negative 5t. And if you pull it out, you pull it out of each term, so you divide each term by negative 5. And I'm like, yes, good. Again, we've got a match. Woohoo! So these are, again, a match. But my arrow is really bad this time. All right. So, more happiness. Good. 2 for 2. We've now verified that these are both solutions. We're done with one bullet point. On to the next bullet point. Verify that these two solutions are linearly independent using the Wronskian. All right. So, now we have to sort of remind ourselves, what is the Wronskian? It's a little bit different here. So we're going to take the Wronskian of these two functions. And these are bold x's here. I know they may not look very bold, but they are. They're bold x's here. So we have these vectors, vector functions that we're plugging in. So how do you make the matrix? Because the Wronskian is the determinant of a matrix. What do you do?
Just take them next to each other and take each other.
So the punchline here for the Wronskian is that these pieces here are the columns. So x1 will be a column, and x2 will be the other column. So when you're making your Wronskian, there's no, I'll take the derivatives, nothing like that. It's just write down the actual matrices, the actual vectors, and the vectors make up the columns. So that's what we'll do. All right. Now, you might look at this and say, this looks like I'm going to have lots of e to the t's multiplying stuff, e to like 2t's, e to the minus 5t's. Can we simplify anything before we start taking a determinant? So, the answer is yes. Yes, we can. And so we want to take a little pause, catch our breath, and talk about the idea of pulling out a common factor. Now, we've already talked about pulling out common factors because we did that when we did our vectors. And it says, hey, suppose all the terms in your matrix or your vector, they have something in common. So you can pull it all out, that common factor. Now, this is the same thing as you can scale. So when you talk about pulling out a common factor, it's like you're doing a scaling by the reciprocal. So notice I have a matrix here. All the entries in the matrix are even numbers. So they all have a common factor of 2. So I'm pulling a 2 out. what's left is I divide everything by 2. So here, these two are the same. So that's for matrices. Now, determinants are a little more interesting. Because it feels like, well, a determinant has something to do with the matrix, so it feels like you should be the exact same. But it turns out there's a little bit of subtlety here. So determinants, you look and say, is there a single row or a single column that has a common factor? So you don't pull it out of the whole expression. You pull it out of a piece of it. So in this particular case, if you look at the matrix we're taking a determinant of, and we know determinant because of the bars here. And on a side note, whenever you see bars, it's really something about size. Size is involved. So you'll notice in this second row, 0, 6, 12, everything is a multiple of 6. So we pull out the common factor of 6 from just that row. And after we do that, well, that row now becomes 0, 1, 2, but the other rows stay the same. So when we're pulling terms out of determinants, we do it either one row or one column at a time. Most often we'll do it a column at a time. Now, why is this true? I think scaling, we're not surprised that for a matrix we pull it all out at once. For determinants, it's a little bit strange. You can prove it using cofactor expansion. There is a geometrical intuition, if you like geometrical intuitions, and if you don't, you can ignore the next 30 seconds. Which is to say that what happens is when you scale a row or a column, you're really just scaling one direction and leaving the other direction alone. Now, if I scale in one direction, remember the determinant is something about area. So the determinant is capturing an area piece of information. What happens if I scale in one direction by, say, a factor of 2? What's happened to my area? It doubles. So when I scale in just one direction, that's the same as scaling just one row or one column. And that's why we have just that fact that you only multiply by 2 and not by some other expression. So that's sort of the geometrical intuition. All right, back to what we're talking about. Before I take this determinant, let's pull out anything that we can to simplify our process. Is there anything in a row or a column that's common? Okay, so the columns have things in common. Now that should be expected because of the way that we construct the columns. The columns are from the functions. The functions have things in common. So from the first column, we'll factor out e to the 2t. From the second column, we'll factor out e to the negative 5t. And then we're left with 3, 1, 2, 3. So we haven't taken a determinant yet. That's still to come. Our future still has fun stuff for us to do. But we're saying these two expressions are equal to each other, and one of them looks simpler for us to work with. E to the 2t times e to the minus 5t, what would that be? E to the negative 3t, because we add the exponents together. The determinant 3, 1, 2, 3. Can we do that? Yeah. Diagonals, 9 minus 2, 7. And therefore, our Wronskian is 7 e to the minus 3t. Now, in terms of information, what are we looking for with the Wronskian? Whether it's 0 or not. So, we have to ask ourselves a question. Is 7 e to the minus 3t 0? No, it turns out not a lot of things are 0. There's only one thing that's 0, and that's 0. And so that says that these functions, namely the x1, x2, are linearly independent. And in terms of our conversation, what that's really telling us is that both of these are giving us information. So in other words, when I have x1, if you also give me x2, it's like, ooh, I've learned more. I've gained something. So the good news of here, we have two good solutions. How many solutions should we have? Like, how many linearly independent solutions should we expect? 2. Why should we be expecting 2? What about this problem says, think 2?
It's the first degree, so there's two ends of one.
Well, okay, somebody says it's first degree, right? That's a first, that's a 1. Someone said, well, look, there's 2 solutions here, Steve, so we should be expecting 2. Should we expect maybe there's a third linearly independent solution? No, we shouldn't be expecting about that.
So multiply the order of the system by the number of spots in the matrix, maybe?
Now, I like some words you have there. You said order of the system. Okay. We might even call the order like size. How big is this? This is a 2 by 2. 2. The size of this matrix tells us something about what we should anticipate. When we have a 2 by 2 matrix, that says we should expect 2 linearly independent solutions. Okay, I'll give you a quiz. What if I had a 3 by 3 matrix? I should expect 3. If I had a 17 by 17 matrix, what should I expect? 17. I should also expect that not to be on the exam, because that's ridiculous. Okay, so the size of the matrix tells us how many solutions we should be hunting for. 2 by 2 says we should be hunting for 2 solutions, and we found 2 solutions, and therefore we say, we found all the solutions. Well, in essence, because these aren't all the solutions, but these help us find all the solutions, which is the last bullet point. So the last bullet point says, write the general solution. Well, once we have a set of linearly independent solutions, and we have the right number of them, which we do, how do we write the general solution? So what do we do now?
Constant times the first matrix plus a different constant times the other matrix.
Yeah, some constant times the first solution, and usually we'll say vector when it's just one column, plus some other constant times the second one. So we could write, for example, A, then we could write 3e to the 2t, 2e to the 2t, and B, e to the minus 5t, and 3e to the minus 5t. And that's a general solution. Every solution looks like that for choice of A and B.
We meant to go back a little bit to our number of solutions. Will we just always use square matrices, and so we can do that rule for all the ones that we're going to encounter?
So the question is, will we always use square matrices, so we can always use the rule? And we can actually answer this. Do we have to use square matrices?
Yes.
People are like, I want to say yes, because I know Steve's going to say yes, but I don't know why. Just embrace your inner yes. Will we always use square matrices? Yes. Okay, good job. Now, there's a good question here. Why do we have to use a square matrix? Well, another way to think about what's going on, do you remember when we did matrix multiplication, we said, well, look at what you have here. You have 2 rows and 2 columns. And then over here, you're going to multiply it by something, and the output is going to be something. Now, when it comes to matrix multiplication, if I have 2 matrices, and a vector is a matrix, what has to match between 2 consecutive matrices? The number of columns here has to match the number of rows. Right? So in order for me to carry out the multiplication, the number of columns in the first matrix has to match the number of rows in the second matrix. Otherwise, you can't do matrix multiplication at all. It's not defined. Okay. Now, this part here is the x. which means that over here, if this is x prime, if I look at x versus x prime, what happens to, let's call it the size of my matrix or the shape of my matrix. Do I add rows? Do I delete rows? Do I add columns? Do I delete columns? Well, when I take derivatives? No, you just do derivatives entry-wise. So whatever the size is over on the one side, it still has to have the same number of rows on the other. So if I have 2 rows here, I have 2 rows there. Now you might say, well, hey, Steve, what about this part? What about the columns, Steve? Well, we usually do it 1 column at a time. But if we had multiple columns, essentially what you can think of happening, you could allow multiple columns. There's nothing that prevents it. But when you have multiple columns, what you're really doing is you're simultaneously solving multiple differential equations, one for each column. And so we have enough time doing just 1 column. So we'll almost always have just 1 column here. Where almost always means always in this class, and usually for most of the classes in the future. But the moral of the story here is because we have to have these matching, that says we have to have a square matrix. I may not have convinced you that it has to be square, but yes, that's why. Okay. Some other notes. We could have done a few things to this expression. We could have factored e to the 2t out. That's perfectly valid. The other thing we could have done is we could have also said, hey, let's throw these together. So we could have said this is the same as 3a e to the 2t plus b e to the minus 5t and 2a e to the 2t plus 3b e to the minus 5t. So we could have put it all together into one vector. That's another thing that could have been done. Which is the correct answer? Yeah, both are fine. They both represent the same thing. Oftentimes, in terms of us looking at it, we usually like to look at them somewhat pulled apart. But both are fine. Okay, so now that we've had our warm-up, we're ready to do a more challenging one. So consider the first order system, x prime, 1 minus 1, 1, 3, x. And this is the kind of thing we're going to be working with for basically the next week and a half. So we want to be comfortable with how we can work with these. And our goal is to develop tools to help us solve these equations. But right now we don't have the tools, but we're going to get close. By next time we'll have some basic tools where we can start to address these kinds of problems. And for now, what can we do? Well, we can verify. All right. Verify that this function x1, it's a vector, e to the 2t minus e to the 2t, and this other vector x2, t e to the 2t minus t plus 1 times e to the 2t, are solutions to this system. All right. Well, let's begin. Okay, so the question becomes, how does one verify? So how do you verify? Do you remember? What do? You plug it in. So to verify something's a solution, you plug it in and say, hey, does it work? If it does, woohoo! If it doesn't, don't. All right. So we want to check, is it the case that x1 prime is that equal, question, to 1 minus 1, 1, 3, x1? We don't know yet. If it was, we'd be done. Okay, so let's take x1 prime. So what's the derivative of this vector? Two e to the 2t minus 2 e to the 2t. Now, in case you're wondering, whoa, how do you do that? There's derivatives. And for matrices or for vectors, one entry at a time. One entry at a time. All right. Well, this one will be a little bit more work. 1 minus 1, 1, 3. And now we have this vector, e to the 2t minus e to the 2t. And here's a point where we can say, we can use this notion of factoring things out to make our lives a little bit cleaner notationally. What has something nice that we can factor out? So the suggestion has been the vector. What's in the vector that's nice, that's common? E to the 2t. So really this is the same as 1 minus 1, 1, 3. Factoring it out, so we factor out of all the entries. It's not very hard because it's a column vector. 1 minus 1. And this constant you can move all the way up to the front. So this is the same as e to the 2t times 1 minus 1, 1, 3, and 1 minus 1. So that way we can simplify and say, oh, we're just multiplying numbers by numbers. In this case, life is good. Okay, so let's see what we get. Actually, we'll go this way. So we have e to the 2t times some vector. Well, what will be in the first entry? So we're going to go along the first row and down that column. So we're going to get 1 plus 1 is 2. Other entry, 1 minus 3. So 1 minus 3 is minus 2. Now, are these the same? Yeah. Are we sure? Yeah, because the only difference is, in one of them we factored the e to 2t out, and the other one we didn't. So these are the same, and so we verified. See, the question was, are these equal? And we can say, oh yeah, we can go the long way around and see that these are in fact the same. All right, so that was not so bad. Okay, so x2, a little bit more interesting. So the question is, does x2 prime equal our same matrix times x2? All right, x2 prime. Oh, well, this will be something. I'm going to give myself a bigger matrix here. So we're going to take the derivative of the first term. What rule do we need? Product rule. And the clue that we need the product rule is that there's a product. Yes, it's a very good clue. All right, so what's the derivative of t e to the 2t? E to the 2t, derivative of the first times the second, plus 2t e to the 2t. The t stays alone, derivative of e to the 2t will be e to the 2t, but then the chain rule kicks in, derivative of 2t brings a 2 down. So that's where the 2 in front is coming from. All right, halfway done because there's 2 entries. Okay, the derivative of the bottom term. Well, that's again product rule. So you can just think of it, leave it at like t plus 1 times e to the 2t. Derivative of the first, derivative of t plus 1, it's 1. So you get minus e to the 2t. And then when we take the derivative of e to the 2t, a 2 comes down. So minus 2 times t plus 1 e to the 2t. All right, well, let's see. Maybe we can clean that up a little bit. Everything has e to the 2t in it, so let's go ahead and pull that out. I think that'll help as we simplify. If we do that, what's left in the top row, or the top entry? 1 plus 2t, beautiful. What's left in the bottom entry? Yeah, so there's a minus 1, and then there's minus 2t, and a minus 2. So we can write that, since we put the 1 in front up on the first, we'll put the constant in front on the bottom. So there's a minus 1, and a minus 2 makes minus 3, and then minus 2t. All right. Well, over here, in the meantime, again, we'll anticipate. Let's go ahead and pull out the e to the 2t. and move it in front, just similar as we did here. So we have 1 minus 1, 1, 3 times t and minus t plus 1. Okay, so this would be e to the 2t. Then we're going to have t minus minus makes a plus, t plus 1. So that's the first entry. Then we'll have a t. And then we're going to have minus 3 times t plus 1. So that's carrying out the multiplication. Okay, t plus 1. What does that equal? 2t plus 1. Yeah, or 1 plus 2t, you might say. T minus 3 times t plus 1. What does that equal? Yeah, minus 3 minus 2t. And what do you notice? They're the same. Verified. Okay. So we've now verified that we have solutions. So verification, similar as before. Plug it in, see if it works. Okay, now another verify. Verify that x1, x2 are linearly independent using the Wronskian. All right. Well, now the Wronskian acts a little differently because it's different than when we went back to our case where we were like, okay, ordinary differential equation, we had a bunch of functions. Now we have a bunch of vectors. And each vector is its own function. So we're trying to look at the Wronskian of these two vector functions, which is really the Wronskian of e to the 2t minus e to the 2t, comma, t e to the 2t minus t plus 1 e to the 2t. All right, do you remember how to make the matrix for this? Okay, there's been a suggestion. Delete parentheses and commas. But yeah, that's the idea. These pieces are the columns. And remember, we're taking a determinant, which we use the straight line to denote determinant. So the first column is the first function. The second column is the second function. So that's the determinant we have to take. Now we can take it as is, or we can say, hey, can we pull out any common factors? All right, we have e to the 2t's. Now, where do we have e to the 2t's? Or, yeah. Now, someone said first or second row. That's true. But where should we really be looking when we look at these things? We should be thinking column-wise. Columns are our go-to object here. And the reason I say columns are our go-to object is that the columns are where the functions are coming from. So we should get used to saying, look in the columns. The columns are going to tell us what to do. And we see, in both cases, there's an e to the 2t in all the entries in the first column. There's an e to the 2t in all the entries in the second column. So we'll pull out an e to the 2t from the first and an e to the 2t from the second. So this is we're pulling out one column at a time. Instead of bursting it, if it had been a matrix, I would only pull out a single e to the 2t because that would be a scaling factor. But this is different, it's a determinant, so be careful. Yes? How do we know what?
How do you know which one goes where? Because if you had an e to the 4t you're factoring out, how would you make sure that at the end you make sure it goes to the right spot?
So, well, we haven't gone to the end yet. Okay. And at the end, what we're going to end up with is not a matrix. We're going to end up with a number. So there's not really any ambiguity about where it goes. Okay. So we're okay.
I trust.
Oh, good. Thank you. Thank you. Takes the time to build trust. All right. So what's left is a little bit easier matrix to deal with. If we were inclined, we could even pull out a negative from the downstairs, but we don't have to. All right. So Let's see if we can't squeeze in the answer in this little bit of space here. Okay, This is equal to e to the 2t times e to the 2t is e to the 4t. All right, we have 1 times this minus t plus 1, which we can say is minus t minus 1. So that's the downward. And then what else do we have? Subtract minus t. Subtract minus t, also known as plus t. And we put that together. Does anything simplify? Minus t, the plus t cancel, and we end up with minus e to the 4t. Now, that's the Wronskian. So the Wronskian is a function. How do you look at the Wronskian and say yes or no? Because the question is, are these linearly independent or are they not linearly independent? What are we looking for? We're looking for 0. If we see a 0, that says, uh-oh, these are linearly dependent. It's not a good set of solutions. But we don't have that. We have something that's not 0. So if we have something that's not 0, what do we say? Yeah, we say, nice. These are good solutions. They're linearly independent. So that's the verification. Okay, so since we're running out of space, we'll get ourselves a new piece of paper here. The Wronskian of x1, x2 is not 0, so linearly independent. And finally, we come to the last bullet point. Write the general solution to this differential equation. So we have two solutions. So both x1 and x2 are solutions. That's the first bullet point. We know that they're different from each other, so it's good to have both of them. And that's the second bullet point. And because we see it's a 2-by-2 system, we expect to have two different solutions. So, since we have two different solutions, we can say, aha, all the solutions have the form some constant times the first solution plus some constant times the second solution, which makes it some constant x1 e to the 2t minus e to the 2t, and some constant c2 times x2, which is t e to the 2t, and minus t plus 1 e to the 2t. You could write this, if you wanted this, as some constant e to the 2t times 1 minus 1 plus some constant e to the 2t. I'm just factoring out common pieces from my vectors here, t minus t plus 1. And that's a nice way to write it. Now, you might say, wait a second, shouldn't I absorb e to the 2t into the constant? And the answer is no, because it's not a constant. It changes. So constants can only absorb constants. Just common factors don't have to be constants. And that's it. That's the first example. Okay, good. Whew. That only took a couple minutes. We'll pick up our speed. Any questions about the process? All right. In that case, let's go up a step. We've done 2 by 2, 3 by 3. So this is going to add a couple of things. First off, a little bit bigger, 3 by 3. Second off, we have this part here. What does that make this?
Non-homogeneous.
Non-homogeneous. Homogeneous would be if we didn't have that. Non-homogeneous is if you have an extra piece on the end. We also have this piece that says x is 0 equals something. What does that say about our problem now? Initial conditions, or we call it an initial value problem. So this is a it's a first order system with 3 equations, which is non-homogeneous and is an initial value problem. Wow. If we can do this, we can do this. All right, true statement. Okay, so again, some bullet points. Verify 3t, 5, 2t is a solution to this system. All right, this has a name that we've been calling it. What are we really trying to show? We had a nickname for this. Well, it's not linearly independent, because really to talk about linear independence, we need to have multiple things. All right, there's a... It's a particular solution. We're just trying to show it's a solution. So we call this our particular solution. Because remember that when we're dealing with non-homogeneous differential equations, we got to work our way up. We say, okay, solve the non-homogeneous part. And then we flip over and say, all right, now let's work on the homogeneous part. That's what we're going to do in the second bullet point. All right, so we're going to think of this as our particular solution. So let's just check a couple of things. What is xp prime? (302). Just go through, take the derivative of each piece. Boom, boom, boom. No problem, no problem. Now the question becomes, is this equal to, question, this matrix 3 minus 2, 0, minus 1, 3, minus 2, 0, minus 1, 3, times our vector xp plus this other stuff on the end. Okay, so, well, we're going to go through and check. 3 minus 2, 0, minus 1, 3, minus 2, 0, minus 1, 3, and we replace what we think is our answer, 3t, 5, 2t, and we're adding minus 9t plus 13, 7t minus 15, minus 6t plus 7. All right. So let's work it through. So we're going to do some multiplication here. 3 times 3t, 9t, minus 2 times 5, minus 10. 0 times 2t, 0. So we would have 9t minus 10. That's the first entry. Minus 1 times 3t, minus 3t. 3 times 5, 15. Minus 2 times 2t, minus 4t. Put it all together, we get minus 7t and plus 15. Last entry. 0 times 3t, 0. Minus 1 times 5, negative 5. 3 times 2t, 6t. So we'll have 6t minus 5 in the last entry. And don't forget, we're still adding that to minus 9t plus 13, 7t minus 15, minus 6t plus 7. So we're adding two vectors together. How do you add two vectors together? Do it entry-wise, right? One entry at a time. So if we add 9t minus 10 and negative 9t plus 13, what do we end up with? 3. Minus 7t plus 15, 7t minus 15, add those together, we get 0. 6t minus 5, negative 6t plus 7, 2. And now we look at this and say, are these the same? They are, they match. And so, solution. We can even be happy with that. All right, good. Progress, progress. We've verified it's a solution. We have something to tackle the non-homogeneous part. Life is good. Okay, well, go to our next bullet point. Verify that these are linearly independent solutions to the homogeneous system. I suspect we're going to need a second page, maybe a third page. All right, well, which one should we do first? Verify that they're solutions or verify they're linearly independent? You want to do linearly independent? Okay, so let's give these names. We'll just call the first one unimaginative names, x1, x2, x3. How's that? So we're looking for the Wronskian of these three vector functions. So that's the determinant, 2e to the t, 2e to the t, e to the t, 2e to the 3t, 0, minus e to the 3t, 2e to the 5t minus 2e to the 5t e to the 5t. Well, before we take this determinant, what can we do to make our life happier? Yeah, we can pull stuff out. What can we pull out? Okay, e to the t from the first column. Okay, e to the 3t from the second column. And pull out e to the 5t from the third column. We could pull out other things. For example, we could pull out 2 from the first row and 2 from the second row. We don't have to. No one seems excited about that, so we won't do it. Okay. 2, 2, 2, 2, 0, minus. I'm just pointing out we can. I'm not saying we have to. But this just, if we pull out the e to the t's, it's going to make it a little bit easier to write down what happens. Okay, so e to the t times e to the 3t times e to the 5t. If we put all those together, how many do we have? E to the 9t. That's good. Now, this determinant looks like one we could actually do pretty quickly, right? So just do diagonals. 2 times 0 times 1. 0. 2 times minus 2 times 1. Minus 4. 2 times minus 1. Minus 4, right? Because I'm just going diagonals. Okay, other diagonals. 1 times 0 times 2. 0, but we're being subtracted, so it's really minus 0. That's a very small amount of humor. That's almost zero humor. Okay, minus 1 times minus 2 times 2. It would be 4, and then we subtract it. 1 times 2 times 2. 4, and then we subtract it. And so put it all together, what do we end up with? We end up with minus 16 from this determinant of this small matrix, and then don't forget, there's the e to the 9t. All right. And what do we observe about this function? It's not 0. Woohoo! Nice. So that verifies the linearly independence. What do we need to check now? Okay, solutions. All right. Well, let's start. So remember, it's the homogeneous part. When we're doing the homogeneous part, we only need what's in the pink box. This piece on the end, that's the non-homogeneous part. So we're ignoring that for right now. Okay, so we'll go through and just work these out. We'll try to do this at a little bit of a pace here, so we can get used to, like, for example, if we were in a test, and we're like, oh, quick, we've got to figure this out. So, x1 prime. What is x1 prime? All right, 2e to the 2, 2e to the t, 2e to the t, e to the t. Now, some people are like, Steve, that's just x1. No, it's x1 prime. Because, of course, e to the t is really cool. Derivative of e to the t is e to the t. Okay, our question, does this equal question? That's supposed to look like a question mark. There we go, that's a little bit more question mark looking. Again, we can pull e to the t out. So I'm going to pull e to the t out. And then we have this 3 minus 2, 0, minus 1, 3, minus 2, 0, minus 1, 3, times 2, 2, 1. So e to the t times 2, 2, 1, that's our x1. So I just pulled the e to the t out. All right. Well, that's e to the t. Quick check. 6 minus 4 plus 0, 2. Minus 2 plus 6 minus 2, 2. 0 minus 2 plus 3, 1. Well, are these the same? Yes. All right, I'll just make it a little long here. This is x1. Okay, so that's the verification that x1 is a solution. All right, x2. Well, what's x2 prime look like? 6 e to the 3t, 0, negative 3 e to the 3t. Does this equal? That's what we're trying to figure out. Again, we'll factor out e to the 3t is a common factor. We have our same matrix. And we multiply that by what happens after we pulled out. 2, 0, minus 1. So that's e to the 3t. All right, 6 plus 0 plus 0. Oh, I can do that one in my head. So that's 6. Minus 2 plus 0 minus 2. So that's plus 2. 0. Yeah, minus 2 plus 2 cancel. 0, 0. I'm liking this one. Minus 3. Do they match? Yes, they match. Good. Solution. Solution. Okay, 2 down, 1 to go. x3. All right, determinant of that will be 10 e to the 5t minus 10 e to the 5t, 5 e to the 5t. All right, is this equal to? Again, I can pull out e to the 5t. We have our matrix here. And our original function, if we pull out e to the 5t, gives us 2 minus 2, 1. So we have the e to the 5t in the front. Okay, 6 plus 4 plus 0 gives 10. Minus 2 minus 6 minus 2 gives minus 10. 0 plus 2 plus 3, 5. Do they match? Yay! That was a half-hearted yay. But we'll accept it. We'll give full credit for that yay. All right. So that's the verification of solutions. And something interesting has happened here, which we'll point out maybe in a few minutes. Okay, so we've now done the second bullet point. Our last bullet point says what? Find x. Cool. Find x. All right. It can't be hard, right? It's like, there it is. We found it. No. That's not what we mean by find x. Okay. So, in general, what would x look like? Okay. It's a combination of the non-homogeneous pieces and what else? And the particular solution. And they already gave us all the pieces. So we have some constant times our x1, some constant times our x2, some constant times our x3, and this last thing, our particular solution. Okay. So, now are we done? There's something we hid. There's an initial condition. Just when you think that you're done, the problem pulls you back in. All right. So, remember, we have this initial condition, x of 0 is 8, 21, 0. Okay, so how is this going to help us? What is this initial condition going to help us do? Really, what are we trying to do? Yeah, what we don't know are these 3 pieces of information. And you might say, well, wait, do we have 3 pieces of information? And the answer is, yeah, there's 3 entries here. So there's 3 entries. That gives me 3 pieces of information. There's 3 things I have to solve for. So we're going to plug in 0. All right. So at time equals 0, we have that x of 0 is 8, 21, 0. because that's what our initial condition tells us. What else is it equal to? Well, what happens when we plug 0 into this first function? 2, 2, 1. What happens when we plug it into our second function? 2, 0, minus 1. Into our third function? 2 minus 2, 1. Into this particular function? 0, 5, 0. All right. Now, this part may not look so clear what to do. But we're going to rewrite this a little bit and say, okay, that's slightly less unclear what to do. All right, so a few things. I can move the 0, 5, 0 over to the other side. So think of it as subtracting, because we're going to subtract it. 8, 21, 0, subtract 0, 5, 0. What would that give us? 8, 16, 0. Okay. So, well, I don't want to write that all down. Okay. Let's look at the entries. And so in particular, we should think of it as there's the first entry, second entry, third entry. In the first entry, we have C1 times 2, which is 2C1. Here we have 2 times C2. Here we have 2 times C3. And here we have 0 equals 8. So that equals 8. So I'm reading off what's happening with the first entries. 2C1, 2C2, 2C3, and 0 gives me 8. Yes? Yeah. Don't worry, there's more to come. This is not the end of the story. Middle entries, second entries, 2C1 plus 0C2, so we don't write that down, minus 2C3 plus 5 equals 21. Well, I can move the 5 across, and that gives us 16. Last entries, C1 minus C2 plus C3 equals 0. All right, well, what do we have here? 3 equations, 3 unknowns. Nice. Now, here, there's lots of ways to do this. So we're going to do it in a way that probably is sort of the least intuitive, just because that's how the other class is doing it, so we'll do it with them. But there's actually some logic to it. And this is for all you linear algebra fans out there. Now, this is a great problem. Look, I broke out a third piece of paper. 3 pieces of paper. Think how many trees sacrificed their lives so we can know the answer to this question. All right. So, one way we can think about this is we can actually think about it in the following way. This is like a matrix, 2, 2, 1, 2, 0, minus 1, 2 minus 2, 1, times C1, C2, C3 equals 8, 16, 0. You can verify it's the same thing that we have. Just carry out the multiplication. 2C1 plus 2C2 plus 2C3 equals 8. 2C1 plus 0C2 minus 2C3 equals 16. Systems of linear equations become matrices. We can rewrite it in that way. Now, in the back of our mind, using the language we've talked about, if I call this matrix for a moment A, and I say, I want this by itself, what would I want to do? I would want to move A over there. Find A inverse, right? So if we were to multiply both sides by A inverse, we would have the C1, C2, C3, and we'd be done. Now, we're not actually going to do that. We're going to do the equivalent of that. So do you remember how we find inverses? We talked about it before. The idea was to do what? You start by writing your matrix, and then you put the identity. And that found the whole inverse. We actually don't need all of it. So here's how it turns out you can do this problem. So you're going to do something similar. You start by putting your matrix A. And now, instead of putting the identity here, you just say, what do I want to take and multiply the inverse by? So in this case, 8, 16, 0. And our goal is, make this I. And if we make this part I, we'll get C1, C2, C3. Because the same process that makes this I is what would have us multiplying by the inverse on this side. All right, so in the few minutes we have left, what can we do? We can divide the top by 2. If we're just feeling giddy about dividing stuff by 2, what else can we divide by 2? Yeah, so remember our steps are, we can multiply any row by a constant, we can swap any rows, and we can add multiples of one row to another. Okay, so this becomes 1, 1, 1, 1, 0, minus 1, 1, minus 1, 1, and we have 4, 8, 0. All right. Now, if you're thinking methodically, work a column at a time. Say, I want to make this look like the right thing. What's the right thing? 1, 0, 0. Okay, so how can I make this look like 1, 0, 0? So I can multiply the first row by minus 1, add it to the second row, multiply the first row by minus 1, and add it to the third row. Yes? If that happens, we don't change the first row, but we do change the other 2 rows. What does the next row become? 0, minus 1, minus 2, 4. Okay. Remember, we're subtracting the first row by minus and adding it to the second row. So minus 1 plus 1, minus 1 plus 0, minus 1, minus 1, minus 4 plus 8. All right. Bottom row, what will we have? 0, minus 2, 0, minus 4. Yes? All right. What are some things we can do now?
Flip the third and the second row and divide the previous third row by -2.
Okay, so this row is looking pretty good in that there's only one place where there's a non-zero entry. So if you can imagine, multiply it by -1/2. That makes it a 1 there. And then swap. So swap, multiply by -1/2, multiply by -1/2, swap. In the end, it doesn't matter. Those are interchangeable operations. So we haven't changed the top row. The new middle row will become what? 0, 1, 0, 2. The bottom row will
0, minus 1, minus 2, 4.
4. Okay. Now, remember, when we're trying to make things look like the identity, it's good if you don't have a better plan. It's actually a pretty good plan. Work one column at a time. All right. What can we do with this middle column? We can add straight up to the bottom column. And what else can we do? Subtract from the top. So the middle column hasn't changed. Let's do the bottom. What does the bottom become? 0, 0, -2. 6, because we're adding. What does the top become?
1, 0, 1, 2.
All right, we're getting close. What's the next thing we should focus on? So we're on to our third column. If we really want this to be 0, 0, 1. So, okay, multiply the third one by minus a half. 1, 0, 1, 2, 0, 1, 0, 2, 0, 0, 1, and what? Minus 3. We're almost there. What do we need to do? Subtract the bottom row from the top, which gives us 5, 0, 1, 0, 2, 0, 0, 1, negative 3. Now, the end process here, this is C1, this is C2, this is C3. Are we done? Well, we're really close. We come back here, because our time is almost over. We just replace. So C1 is 5, C2 is 2, and C3 is negative 3. And that is our answer. And yeah, that only took the whole class to do 3 examples.